Here's the solutions to the problems for chapter 4, the first few sections where it's projectile problems. Again, I don't think this should be anything horribly new, so hopefully you're able to figure these out. Um, Problem 1 was just asking for the displacement if something had both a vertical and horizontal acceleration. So you can get the resultant acceleration. You don't really need to use I hat, J hat, K hat, stuff like that. It's okay if you do, but you don't have to. I get 6.2 meters per second squared, and I plug that into a formula for position of an acceleration object, or displacement rather. I get 111 meters. Problem 14 I kind of like. It's a plane trying to send supplies down to people, and they want it to land right on them, which is a little annoying, but anyhow, you want it very close. And the plane's moving 150 meters per second, and it's very low, on only 100 meters above the ice. So the first thing we do is we want to find out how much time it takes for this to fall. So you can use y equals 1 half gt squared, which is a version of a formula on your formula sheet. And I get that it takes about 4.5 seconds to fall. Once I know that, if I know the horizontal speed of the plane, which is going to be constant, I multiply that by the time, and I get that it's about 678 or 680 meters. So if the target is here, mark it with an X, then you need to release this 680 meters before you get to that point. This is how bombing works, honestly. So back in World War II, there was a famous piece of equipment called the Norden bomb sight. It was used to kind of do some of those calculations. So basically, if you knew your altitude and the speed of the plane, then when you released your bombs, you could sort of program that information, and it was to try to guide them to the target. And unfortunately, air resistance is pretty complicated, so they were not nearly as accurate as the laser-guided weapons of today. For problem 43, basically is giving a problem of somebody hitting a golf ball on Earth and the Moon, and it's asking how far it goes, much further it goes on the Moon, and how much longer it would be in the air in terms of time. So I use this equation, which works if something lands at the same height as it's launched, to find the horizontal displacement. I got 55 meters on Earth for the speed that it was hit and the angle it was hit. On the Moon, I got 332 meters. So it's actually 6 times as long, since gravity is only 1/6 as much, and that's in the divisor. So in this case, the time I can find by looking at the change in vertical velocity divided by a. So if this is at a 30-degree angle and the initial velocity is 25 meters per second, that means the vertical component of it is 12.5 meters per second up, and then when it lands is 12.5 meters per second down. So basically what we've end up having here are two different equations that look the same on the top, but in the bottom they have different denominators. Again, the Moon's gravitational pull is only 1/6 as much. So therefore it's going to be in the air for 6 times as long. So the same delta V, but over 1/6 the gravitational acceleration. So that ends up being about 12.8 seconds longer in the air. So I wanted to look and show you why those things were 6 times as much on the Moon as on Earth. That's because the denominator is the only thing that changes in the equations. When I go down to number 44, this is a problem where you have something shot, 60-degree angle from horizontal, shot at a certain angle, and it's in the air 4 seconds before it lands on a cliff. So first thing with the projectile problem I do is split up into vertical and horizontal components. If you're asked to figure out how high this cliff is, I can put that the final vertical displacement equals the initial vertical height plus VOT plus 1 half AT squared. And all these are only vertical numbers. So that VO is not 30 meters per second. It's basically 30 meters per second multiplied by the sine of 60. So I end up finding actually that after 4 seconds, if there was no gravity, it would have gone up 104 meters, but gravity's pulled it back down 78.4 of those. So the net height of the hill, or the edge of the cliff, is 25.6 meters, about 80 feet. The maximum height, I can look at and say that the final velocity as something is shot up is going to equal 0 meters per second vertically. The initial vertical velocity was 26 meters per second, and the acceleration was 9.8 meters per second squared down. So I can plug that into this kinematics formula, and I get that the change in elevation to the max height would be 34.5 meters. For part C, it's asking the final speed at which the object hits when it lands on the surface of the cliff. Well, the horizontal speed isn't going to change. It's going to be 15 meters per second. That's why I have all these scratches out over here, is I'd put 18 in, and I don't know why, because I'd already written 15. At any rate, the final vertical velocity is actually going to be downward at 13.2 meters per second. I can use VF equals VO plus A times T. Again, only thinking of vertical information. It was shot up at 26 meters per second, but gravity is pulling it down at 9.8 for 4 seconds. So the final vertical velocity is down 13.2. So again, think of this as basically being a Pythagorean theorem here. 15 horizontal, 13.2 down vertical gives me a resultant speed of 20 meters per second. For 49, I like this problem because it's kind of going down at an angle, and that's not something we tend to see very often. And it says that you've got sand coming off the edge of a conveyor belt. Could be sugar going into like bags that you would sell at the grocery store, stuff like that. And it says it's falling 3 meters vertically, and you need to find how far away this should be from the edge of this filling pipe. So that's a horizontal distance. So as always with projectiles, I'm splitting this mathematically into horizontal and vertical components. So the first thing I want to do is find the time it's going to take for this stuff to fall in the pipe. So to do that, I need to think about this as a 3 meter vertical height. I know my initial vertical velocity is downward at 1.55 meters per second. I know the acceleration due to gravity as it's going down, and I know how far it's heading down vertically. So when I think about that, I can find the final vertical velocity right before it hits in, which is 7.82 meters per second. And so then, therefore, now what I can say is to find the falling time, I take t, it's going to change in vertical velocity over g. So I found my initial vertical velocity downward by using trig, that was 1.55. Found my final vertical velocity downward due to kinematics equation, that's 7.82. Since it's accelerating at 9.8 meters per second every second, put that in the denominator, I get about 0.64 seconds. So when I multiply that time by the horizontal speed, which is 5.8 meters per second, I get that this thing should be placed about 3.7 meters away from the edge of where the material is falling off. That was pretty quick. If you have any questions, let me know.